Okay, let's get started. 7:30. We have 72, 74 participants. That's quite good. And we'll have the review today. Let me hit the record button first. Record on the cloud. Okay. So we'll do the review for the midterm, which is upcoming on this next day, right? Monday, yeah, 14. So for that, we have this discussion topic requested from you, and I have some responses from here. I can see many of you wondered about the state of the ALU, sequential ALU. We'll definitely go over that. Like one, I think there is one from Lockpreet on the same topic. There is one specific explanation needed for the problem 8. There is one from Caleb. Caleb, have you looked at? I have opened up the answers for the quiz. So you
yeah,
should.
I looked at those.
So if you have any further question, you can ask me actually.
All right.
Okay, let me take Andy's question first. Andy asked how to build a decoder and multiplexer that are not multiplier of the most basic form. So Andy, what do you mean by that one? Like not most basic form? Can you give me an example? Like
your line decoders usually, or the ones you have in your presentation are like 1x2. Like the multiplexers are 4x1. And it's easy to like build a 2x4 decoder, for example, because you can just kind of multiply everything by 2 and figure that out. But like for the non-traditional ones, like 3x8 line decoders are like, I don't know, 8x4 multiplexer or whatever. Like how are you supposed to build this?
Multiplexer side, there is nothing like on the output side, there is nothing like more than 1. So let me explain that. What is those X symbol means? Okay? So probably that will clear up the confusion here. So your let's say this is like something like M cross N. It's usually mean M number of input and N number of outputs. So that means like, so your thinking is this, like, what if I have been given 5 cross, let's say 3, something, right? Now let's see if this can appear or not. For the multiplexer side, mux is a component which always have output of 1. It can be multi-bit. I can ask you like this can be a 32-bit output, but still it's a one single output, and it can operate on independent selection line, which can independently be 32-bit itself. I0, I1, I2, I3, and there will be like selection bit S0, S1. So it will still be 4x1 mux. It may be 32-bit, which means like my input selection lines are individually, not selection line, input options for me to select between would be each of them 32-bit, and output is also 32-bit. So there can be like, let's say 5x1 mux, right? Or 7x1 mux. I think Andy's question is that how do we construct corresponding decoder, right? I'll come to that part. Let's look at the decoder side. So decoder, especially the line decoder, line decoder is in the form of, like, if you want to say like m multiplied by n kind of stuff, it's practically is m multiplied by 2 to the power m. So 3 by 8, 2 by 4, 4 by 16, 5 by 32. So you'll see this part, output for the decoder is line decoder. For our discussion is always 2 to the power something. And that's only then you can actually make the circuit. Otherwise, if someone gives you a line decoder of maybe 3 to 6, like this is not line decoder, just decoder 3 to 6, then what is the truth table going to be? We don't know. For that case, one must provide you the truth table of this guy for you to construct a circuit out of it. Unlike the line decoder, if someone wants to give you a line decoder of 4 by 16, we pretty much know what the truth table is. It's practically exhaustive of every combination of 2 to the power 4 combination of input side, and its output is the corresponding minterms. Make sense, Andy?
Yeah. So how does that relate to the like 7 times 7x1 and 5x1 mux?
Okay, so yeah, now come to this question, 7x1. Now that 7x1 means you are trying to generate at least 7 different minterms, right? Different minterms. So how many inputs for the decoder would be for the 7? Like if you look at this one, so we look at the output side and we're going to come to the input side. So for that one, that means we have this relation between n and m. M equals log base 2 of n. Yeah, ceiling. So in this case, my n is 7. So my m would be ceiling of log base 2 of 7, which is 3. So practically you are looking for 3 by 8 decoder in this case. You will only use 7 minterm out of it, right? So the thing is, like, what does it mean in terms of design now? So when we are talking about 7 by 1 multiplexer, we are talking about 7 different inputs here. Let's say maybe I0, I1, I2, I3, I4, I5, I6, and output Y. And we need to have a selection signal, 3 selection signal here, which gives me like 8 combination, right? So in that case, we must specify which one is the selection combination. So valid selection combination, 0, 1, 2, 3, 4, 5, 6. That means for these guys, selection 7 is invalid. Like there is nothing like is connected here. Or we can actually do other way, like we can start from 1, 2, 3, 4, 5, 6. So we can actually make this circuit which picks up 1, 2, 3, 4, 5, 6, 7, and in that case 0 is my invalid selection for this mask. However, in standard, this generally comes as a power of 2. Generally, this is power of 2. Andy, make sense?
Yeah. So you wouldn't see like a 4 times 8 line decoder, right?
4 times 8 line decoder without a truth table doesn't make any sense.
Okay, that makes sense. Thank you.
4 by 16 makes sense because we know exactly what the functionality is. Not like a 4 by 4 or 4 by 8 kind of stuff. Okay.
Professor?
Yes.
So internally inside of that multiplexer, is it still internally using a 8 by 3 line decoder?
3 by 8 line decoder.
Yeah,
yes.
3 by 8. Is it still using that?
Yeah.
And is it just like one of those minterms on the output side is not connected to anything?
Yeah, exactly.
Oh, okay. So it's like the decoder, you just don't use that last like minterm 7, and then you just do like ands between the first 0 to the first like 0 to 6 minterms.
Right.
Selection bits.
Yeah. And it need not to have to from very fast one to the next consecutive one. You can pick your choice of invalid selection and just don't connect it.
Yeah, and if they use, so theoretically, if you use that invalid bit, it will always result in 0, right? Because
it will always result in because it's always going to be all 0 in that case.
Yeah, because all of the, like, if it's that minterm, then all of the other outputs of the decoder are 0. And if you and all of those, and if you do an AND operation with all of those selection, with all of those like input bits from the actual multiplexer, then all those ANDs will result in 0, which when you do an OR operation with them will also result in 0.
Exactly. Your thinking is exactly correct. And thank you for bringing that up. Because that gives me the idea of trick question in quiz. Thank you.
You're welcome.
Whoa.
No, friendly.
No.
I'm sorry.
No, but I like this kind of thinking. That means you guys are analyzing this really from inside out, the functionality, what is going on. And that exactly we look for as your understanding, basically. Okay. The next one is, so this one is done. Okay, let me come to this fan's question, problem 8. Okay, problem 8. So these type of problems, let me see, am I sharing screen? So you guys can see both the windows, right? Jamboard and the web page.
Yeah.
Oh, okay, so that means I'm sharing the screen. That's good. Okay, so this is about this problem. This number 8, which states, let me open up the question as well, which is like this one. So question number 8 is this one. How many basic logic gates of 32-bit triple carry? Huh? Is it? Oh, yeah. Let me make sure. Number 8 of set, problem 6. Okay, 6, 8. Number 8, okay. So it talks about basic logic gates. We did a similar thing with a NAND only, and that's basically NAND only gives more consistent result. If we talk about a basic logic gates, answer can vary, by the way. That's what, if you look at the last footnote of this thing, yeah, it can be depending on your transformation of the logic expression using 2-input NAND NOR or not, your circuit and component count can vary. But it's basically exactly this one. So this one is more like we are deriving things out of this sum and carry bit. So it is now our choice, since it does not restrict us for any type of NAND or NOR specific gate. You can use any basic logic gates there, which is not NAND NOR. Then we have these expressions, like it's a Boolean expression that we derived in that corresponding lecture. Please see the note that your sum bit is ultimately this, and then carry bit is let me see, replica adder. Yeah. So what we are doing in this case, sum and carry. Yeah, carry is this one. So we are transforming this thing for usage of basic gets. So what would be like in this transformation, we use De Morgan to transform into a more suitable form like this. So it really depends on how you transform things. So this guy, then I can determine this guy is a NOR where this B bar is an inverter. So that's what we are counting. So we need 4 NOT basically, A bar, B bar, CI bar, this one, and the whole. Okay, so here what I'm trying to show you which part of the expression is using the inverter. Okay, just to like highlight the part, and the rest of them are coming from the inside logic. So that is the 4 NOT count. And then we are counting the NOR individually. So this guy, all this highlighted one. And then what I am showing is basically this part is also a NOR. Practically it is NORing between result of the inner NOR. So that's what I am showing here. Maybe that was the part of the confusion coming to you, that how this is represented. So this is just for, like to explain how you count the gets into from a given logic expression. Okay, so that's why we count it. We come up with a 9 NOR there. And then we talked about, I think there is a confusion. This is not Y, this is C really. I think, let me see. CIA or BAB, right? CIA or, yeah. This is the carryout. So please make a note. This is a typo. This has to be C, not Y. So in that same fashion, I try to transform this get using De Morgan and whatnot into some more manageable expression with the basic logic gates expression like a NOR, inverter, NAND, etc. So then we basically go and analyze this expression and find out how many NOTs we need for this one. We're not counting A bar, B bar for this NOT count because we already had this for the other part, right? So we will reuse them. So we really specifically need one more extra NOT here and 2 extra inverter, NOR gate here. And then we are counting together. That gives me total of 160 NOT gates and this many NOR gates, etc. This makes sense. Just general outline of how do you compute that, Ms. Fan?
Yeah. But the last time when you solved it, I remember that we used the diagram. So could we use the diagram for this problem too?
This one? Yeah, sure. You can. You can, yeah. I was too lazy to draw the diagram here, so I went with the expression.
Professor?
Yeah.
I think she means that like, can we just like draw the diagram in terms of, so we have this, we have like the full adder, and in a full adder we have 2 XORs and 2 ANDs and 1 OR, and then we deconstruct those into the NANDs, NORs, and NOTs. Like, can we do it that way? Can we?
Yeah, true. Why not? Because it did not say anything about. Let me see the question. Yeah, it did not say anything about the restriction of if there is any restriction like you need to use minimum number of gates or minimum number of logic. In that sense, you can transform anything like that. Yeah, definitely.
Yeah, but I think this way is like it uses less gates than like doing the diagram way. So if you do the diagram and you do the AND, the XOR, and the OR, and you turn them into the those corresponding gates, it uses more gates in total, I think. And
Right.
also, I have another question. So, in problem 8 and in I think problem 6 too, we're able to use NAND, NOR, and NOT in order to like do the implementation. So I'm just wondering like when we do that, how do we know which gates to use to like deconstruct like the AND? Like if I have AND, do I use two NANDs or do I use a NAND and a NOT?
Anything. So that type of question gives me more work because anything can be a right answer. You know, like that's why I in exam especially I try to stick with a specific type of gates so that the answer is unique in that sense. So if nothing is specified, then you are at your own liberty to use any kind of gates there.
Oh, so if like the diagram or something uses like AND, I can use like two NANDs or a NAND and an inverter?
Yeah, exactly.
Okay.
As long as you explain that okay, I am using for these, I'm replacing AND with a NAND and an inverter, I'm okay as long as there is an explanation.
Okay.
Yeah. So that's why I also mentioned in this problem as well, like it can be different depending on your transformation, how you're solving this problem.
Also, can you scroll back up to the equations, the initial equations for problem 8?
Mm-hmm.
Okay, so like for the carry out, I'm not sure if it should be A plus B, like inside the parentheses, or ending with the carry out. It shouldn't be like A XOR B.
Maybe I cannot tell right now on top of my head, but maybe can you please send me a note? Here, I'll double check tonight.
Okay, I'll send you an email.
Let's see. XOR B. Okay, I'll check. Let's not hurry up on that part.
Okay.
Okay. So next one is the ALU. Okay, ALU. So this one we were studying it in our class. One of the video lecture has this. This is just one proposal of how the ALU, sequential ALU should look like. Remember in our project and in our instruction set that we are dealing with in this class is devoid of the function divider. And we are implementing multiplication in a combinational way. So this is specifically to avoid to implement a sequential ALU, which is a little bit tricky and which does not add much experience on top of what you are doing as a hands-on projects in this class. So that's why I simplified it. But in reality, your ALU actually provides the division operation, multiplication operation done usually in a sequential fashion, unless it is a very specific application hardware where multiplier is given as a combinational multiplier. So in that sense, this whole ALU picks up a clock, and definitely it has a reset preset signal of this so that we can start with a specific state of this ALU. And like the combinational ALU, it picks up two operands of 32-bit each. Let's assume that. And it has two 32-bit output to cater the 64-bit result, like a multiplication result or a division result. Well, when we have two results, remainder and quotient. So for that scenario, we have two output coming out of this ALU, and also another output called a done single bit signal, which is basically telling that, hey, my operation is done. Then whoever is looking for the result, they can pick up from the output of the ALU. So that's the down signal purposes. Now this state, this is a very simple state diagram machine, and we need to go for the state diagram because the division and multiplication operation, even the shift operation in this data path, you can see they are all sequential circuit we deploy. So multiplier is sequential, divider is sequential, shifter is sequential. And each of them has their own state machine. Remember, multiplier has a controller. That's in turn, that's a state machine. Divider has a controller that is also a state machine. Shifter is also a state machine. So they are very simple state machine, but nonetheless, they are state machine. So, so that means my overall ALU needs to have a state machine, especially to control when to get out the result out of the door and the down signal out of the door, when to do that. So that's the purpose of this state diagram of the ALU, which practically depends on my input is the operation code and the down signal. Now, what does that mean? Like down is going out, but how do I make sure that why I'm depending on the down? It's basically to synchronize the state between this ALU and the rest of the sequential element like multiplier, divider, and shifter. So these are the two inputs, my operation code and the down signal itself. And the output is my shift, not and. Okay, outputs are what? Oh, okay. So these are the commands to the different part, right? For example, adder subtractor, it has these control signal for whether it is a subtraction or addition. Then shifter has a control signal whether it is a left shift or right shift, when to load the pattern into the shifter, when to start this shifting operation. Similarly, divider and multiplier, all it has also have this load signal to load the data into and start the operation at certain point of time. So those controls are coming out from the ALU controller, and that issuing of the signals depend on this ALU controller state. So this ALU controller start with let's see, start with these start state, which like upon reset it also goes into that state. And as long as operation code is 0, so this is first 0x, this one is your, let me see if I can annotate. Okay. So this one is your input, and this part is your output. So it's saying that as long as my operation code is 0, I'm just at that state. Okay, nothing is happening. But as long as my operation code becomes 3 or 4, it went to a state called MD, which basically is reserved for a multiplication division state. So when it is transitioning to that state, it basically giving the start signal to 1, keeping the load to 0, and LNR doesn't matter. Okay, and it is assuming, by the way, it is keeping the load signal to 0 means it is assuming divider and multiplier is actually looking at those data, incoming data part. So if I go back before this guy, okay, so here, so look at this, operand 1 and operand 2, they are directly connected to the multiplier. So this guy is assuming as long as the controller is issuing the start signal, it loads those patterns. So it doesn't have a specific load into that multiplier or divider, load control signal. So that's the assumption of this thing. So that's why we are seeing that start as 1, load at 0, and we are basically don't care about whether it's a shift right, shift left, or addition, subtraction, because these are not that operation. So it goes into that state and stays there till my done is 0. Okay, my done is 0. Oh, what happened? As long as the down signal, which is coming out of the every of the sequential divider multiplier as a down signal, as long as they are 0, we are stating just staying at the multiplication divisions, assuming those individual multiplier divider actually acting on the data and crunching the result. So as soon as my done is 1, okay, I basically set the start to 0 and keep the load at 0. Other control signal doesn't matter from this side. So I come back to the start signal. That means essentially my multiplication is done. Similar way, if it is my operation code is 1, I go to add with issuing the SNA. This is an important thing, SNA. We need to set to add mode. I don't want to accidentally start any sequential element. So sequential design stay put there with a start 0, load 0, LNR, I don't care at that point. So it can be any logic value. So it goes into the add stage and waits there till adder gives me a down signal. So when it is a down signal, then it comes back and just keep the start signal at 0. Other control signal doesn't matter at that point anyway. Similar with the 2-8 subtraction and set less than, but in this case, this SNA is set to 1 for a subtraction mode in the adder, and keep these two at 0 so that we don't start the sequential elements in the data path, and we don't load the shifter unnecessarily. So we keep them at 0, 0, and stay there till my done is 0. Once done is 1, we just come back and set the signals accordingly. So we have similar for the shift right. For here, important is that when it goes into the shift right or shift left, depending on the operation code coming to the ALU, when it is coming there, then it is keeping the start signal 0, but turning on the load signal, So this load signal, what will do, it will load the pattern to be shifted on the shifter circuit. And then once it is done there, until it is not done, then it will turn on the start signal. So this is a little bit different than the multiplication, division, sequential operations there. So it's basically one stage, one cycle, it loads the pattern into the shifter and then start it. And so once it is started, it stays there until shifter say I am done. And once it is done, it goes back to the start state with the start and load setting to 0 so that no new operation is started at that point. So similarly for the SL, and logic is the same as an adder subtractor less than operation, because these are all combinational. It will just come back in next cycle. It will just come back in next cycle to the start state. Sequential part is this guy, and this guy, where it basically effectively waits onto that signal. So this makes sense?
Yep.
So do you mean for professor?
Yeah.
So you mean for like shift right and shift left? once it goes into the shift right or shift left state, it has to wait one cycle before uh, the signals actually change to like load to like start and like LNR. So start and LNR
Yes.
happen
Yes.
on the cycle afterwards, right?
Yeah. So when it is transitioning in that cycle from start to the shift, it basically at that point it is loading, and next cycle it starts its operation.
Got it. Thank you.
Professor Patra?
Yes, Anjali.
I was just gonna ask, would you recommend us to like not memorize, but like have the general idea of like specific diagrams? Because I know we have seen like a lot of different diagrams, like the latches and like the I type, R type stuff. Are there any specific ones that you think we should remember?
I would put that in a different way, like you're thinking. You should be able to construct the data path given the situation. Even like, so that is the target. Instead of like I would suggest not to try to remember thing, but understand how these data paths are constructed. If you are worrying about this so many data path diagram in the lecture 11.
Oh wait, not those. I mean like just in for like in general the diagrams that we've seen throughout lectures like 1 through 11. If there's like any of them that like specifically are like more important to remember, like if we should remember how many.
Remember, like this exam will not have a diagram drawing question, so I don't want be able to ask you that. Okay, show me like flip-flop logic circuitry or derive the circuit and draw the schematic diagram. No, not that kind of question, but definitely conceptually it will help you if there is a uh, now counting component counting type of problem, that how many NAND gates are needed or how many basic gates are needed in the specific circuit. In that case, it would be helpful if you remember. And that's where also, like, not even lecture 11, but let's say you are dealing with a flip-flop, right? So instead of remember exactly what are the connections, output going to this thing, if you understand how that flip-flop structure is derived, then I believe it will be easier for you to draw on paper on spot to solve the problem.
Okay, thank you.
Professor?
Yeah.
Oh, will there be any like diagram questions like the one in the quiz? Like this is a CMOS transistor level schematic for a logic gate.
Or looking at the diagram and inferring something?
Yeah, like would we have to tell what this diagram is? And
Yeah, sure.
okay.
Okay. All right. Let's take 5-minute break from here, 8:15. We'll be back with one specific discussion. I think Catherine requested me in my office hour to go through a little bit over like how this data path control for works in a nutshell. Okay. So I'll try to go over that if you don't have any other question. So let's take 5-minute break from here and we'll be back around 8:15. Okay, 8:15. Let's get back to our discussion. So this phase, what I want to do here, let's pick up a R-type path, R-type data path. Let's see. Okay. So question is like, for executing an instruction, what are the control signal involved and which control signal is issued at what point of time? This is more related to, there is this optional video, right, for the instruction code generation, which also helps you. Like I have explained this instruction control path time to time in the main videos, but the optional video has this hands-on explanation of with a couple of instructions how the control signal would look like at different phases, and that will help you to understand the whole function of these processor internals, and also will help you in the project 2 handling and also project 3, most important on the project 3 side. But the same concept is applied on the project 2 as well. So that part, let me explain very nutshell, very quickly if I can touch base on, because it's a big topic. And in fact, that optional video is almost like an 1.5 hour long with the example from the different instructions. So I would strongly recommend you to at least go through 1 or 2 instructions to understand the whole concept from there. But let me see what I can do in a short time here. And that's why I picked up a very simple like R-type data path without like having complexity of I-type or J-type and combine them together into a very complex data path. Let's keep it simple. Okay, and that will probably serve the purpose of understanding what's need to be done. So let's say this data path will be used to construct some arithmetic instruction, maybe like, for example, like this one. Say 17. Let's say we're trying to do this, add maybe R10, R2, R3. Right? So basically we are trying to read from register R2, R3 and write it back into result to R10. So in this case, remember our state machine is 5 cycle always. Like instruction fetch goes to instruction decode, goes to exe, goes to memory, write back, comes back to instruction fetch. So at that different point of time, your controller needs to issue appropriate control signal to data path to execute this specific instruction. So what are those? So we can possibly make it in a table. Let me just make this diagram a little short. Okay. All right. So what we're trying to do here, we are trying to construct a table with my control signal values, logic values at different phases. Instruction fetch, instruction decode, execute, mem, and write back. Okay. And control signal in this part is these guys. One is definitely my PC load, and ALU operation code, memory read, memory write, register read, register write, this mask selection, this mask selection. I think that's it. So we have PC load, then we have mem R, memory write, then register read, register write. I'm just writing in a short form there. Now ALU selection 1, ADDR selection 1, and ALU operation. So remember, this one is multi-bit, right? And the ALU operation code-wise, I think it is a 4-bit or something 8-bit. We need to check, but some multi-bit. It is not a single operation because the add is possibly encoded as 0000, something like that. This is the add ALU operation code. Don't mix it up with the machine code of opcode of the add. Opcode is different than ALU operation code. You need to understand that part. But nonetheless, we need to look for what are the logics set at the different stages for accomplish this instruction. So first thing is the instruction fetch. So instruction fetch, what we need to do, we need to make sure that my memory is in read mode, memory write is in 0 mode, like is read and write. Register, let's assume at this point, register has only 2 modes, read mode and write mode. Okay, unless it is specifically specified, it has a special hold mode or something like that. We always assume that memories and register, those have only read and write mode. So let's assume that. And the very specific setting, safest setting for the register file in that case is the read, because we don't want to write anything onto the register file, and neither on the memory, by the way. In that sense, we will keep it in a read mode. So we'll pick 0 here. Now, at this moment in the instruction fetch, you see the address selection and the ALU selection doesn't matter. I can set it to any value. So in that case, I prefer to put it 0 because there is no default like safest default value in the hardware world is 0. So set it to 0 if it is a don't care. So at this point, instruction fetch, address selection 1 and ALU selection 1 doesn't really matter. It's don't care. And ALU operation code is also don't care. Okay. So you can put anything there, 0001, let's say. Okay. Or we start with a 0, as we are mentioning. 0 is the safest. And what we'll do, we will assume this guy. Let's assume some other bit pattern. 0010 is for the function ALU operation code for that. Let's assume this. Now, what about the PC load? PC load is definitely, I don't want to mess up with the PC at this point. It's 0. All right. So once we give this, then memory, instruction memory is going to give me the instruction back to my processor. And I go into the instruction decode, and remember this also in register fetch stage. So for this instruction, definitely I need to fetch register 2 and 1. So that means my most important thing is that I need to make it a read mode at this point, definitely. And memory, I will keep it in a read mode. I don't want to write back anything. PC load, definitely I don't want to change at this point. ALU selection and all these stuff are immaterial, don't care. So I put a 0, safest value. Now on the exe time, now it is important that we evaluate the result. So at this point, most important is the ALU operation code. So I will give it the real code now. And also ALU selection is important. I want to select data incoming from R2, not from the shift amount. And because my instruction is add, so that means I need to set the value to 0, selection value. So that's good. Selection value to 0. And address selection at this point is immaterial, just keep it 0. However, the register read and write, because is a safe mode, I'm putting there. And memory read write as these, PC load 0. On the mem side, what I need to do is basically see this is a combinational ALU. That means if I change either ALU operation or any of this data, ALU output is going to change. We don't want that to happen. We want this ALU result to be as stable as possible till this result is written back into the register file. So that means I need to keep my status quo here during the mem phase as well. We need to keep this operation code as this. We need to keep the ALU selection 1. We need to keep the register as a read mode. We'll keep the memory as write mode. PC load as 0, no reading, address selection doesn't matter, and we keep it 0. Now on the write back side, what we'll do, now we want to write back the result into the register file. So at that point, I will need to still keep the ALU operation code because it's a combinational circuit. If I change it, the result can be different. So I definitely don't want to mess up with that. Thus with the selection, I don't want to mess up with that. Address selection at this point, it is important because at the write back stage, I load the PC with the next instruction, which is for this case is PC plus 1. So I need to keep the write back 1 at this point, and I must keep PC plus 1 as my next selection. So this multiplexer selection signal must set to 0. So register, what about memory read write? It's simple, 1, 0 as a read mode. Now I am writing back here. So my register file must go into the write mode at this point. So I make it a 0, 1. So that's how we basically determine this control signal. We need to review what the functionality, what the execution of the instruction is going to be with respect to this 5 cycle, instruction fetch, decode, execute, mem, write back. We set up the correct control signal at correct point, correct phase. Christina, is that make sense?
Professor, I just want to clarify some things. So basically, for your memory register, memory write, even though we don't have any memory operations,
can you speak up a little bit more? I can barely hear you.
Oh, sorry. Yeah. So just wondering for memory operations. So even though we don't have anything to do with the memory, we're still keeping memory read at 1 and memory write at 0 because it's the safest
Yeah.
Okay. So same thing with your register file, right? Even though you don't have anything to do with it, you keep it at read.
Yeah. Yeah.
Okay. Okay.
If problem says, okay, my register file has a hold mode 0, 0, and you need to keep them hold mode as much as possible. Then what you'll do, your relevant, in that point, your relevant important part would be to must read is this one, when you are fetching the register. Other part, you can just keep it at 0. Let's say 00 is hold. Assume 00 is hold in a given problem, like not in this problem so far what we discussed. But in a given problem, it says, okay, we have a hold for a registered mode, which is 00, and you keep the register in hold mode as much as possible. Then you can actually do that. Like, because at this point, at the instruction fetch, I really don't care about the register reading. Only during the register fetch I care about that. And after that, it is anyway hold mode, right? So I can hold it throughout. Oh, what am I doing? I'm talking about the memory, right? Sorry, my bad.
Instruction memory, right? That's
Yeah,
part of the memory.
but I'm discussing about the registers.
Oh, okay.
So just hold on. I just put in a wrong place. Oh, okay. So, okay. So this one, let's register 0. This is 1. Now we are assuming 00 for register. There is a hold mode. And we need to keep it as much as in the hold mode. That is the, let's say the problem says that. Then what you can do, you can make it hold here, make hold here, make hold here, 00. Only important part that you need to read it, the register fetch point, and then you hold it throughout till you are writing it back, right? So it depends on the given problem, but in general, if nothing is given, safest assumption is that you keep it on a read mode, the register file and memory, both in the read mode, unless you are trying to write it. Make sense?
And to clarify too, since like instruction memory, that's part of your memory, right? Yeah. So in the instruction fetch stage, your memory must be set to read, right?
Yeah.
Okay, cool.
Instruction fetch state, your memory must be in a read. Other than that, you can have it in the hold mode if it is there. But if it is not there, you can still put it in a read mode, where what we are assuming in this point, your incoming address is stable, which is true. Like, we are not changing program counter in between till we are in the write back stage, right? So we can keep it in a read mode there. So any other question, Christina? Okay, any other question?
Professor, you mentioned the opcode is different from the ALU operation code.
Mm-hmm.
I was wondering if you could expand on that. I thought they were the same thing.
Not really. Yeah, let me just bring out the notes. Okay, just hold on. They can be coincidental, by coincidence they can be same. Okay, so your addition opcode is all zeros. Addition, subtraction, multiplication are type, right? I'm sharing the screen, right? You can see my slides.
No, we can't.
Oh, what am I sharing? Okay, let me see.
The Jamboard right now.
Oh, okay. Sorry for that. Let me share my screen. Okay, share screen, share. Okay. All right. So here you see this just for the machine code purpose. This is your operation code, and the function code goes here. But if you look at the ALU slide, for example, it can have completely different different code compared to that one. So see, the 1 is addition here, 2 is subtraction, 3 is multiplication, 4 is division. It is nothing coincidental with this guy, isn't it? They're not same. So this is for machine code construction and how the processor understand what instruction is being executed. And then this operation code is for the ALU instructed by the controller to what arithmetic or logic operation it need to perform and give result on. Make sense?
Yeah, thanks.
Yeah, so they're practically, they're different. They're different things basically here, two things. Okay, other questions?
Oh yeah, I have a clarifying question about like the control state again.
Catherine, I told your name at Christine. No, Catherine. Okay, yes.
Yeah. For the like jump register, since it's updating PC, it's done at the right back, right?
Yes, it's
okay, cool.
at the right back. Yeah.
Okay.
It's always done at the right back. The PC update.
Okay.
Professor.
Yes.
What time are your office hours on Wednesday?
4:30.
Okay, thanks.
Okay, so you can actually, then it's the same extension of the same like same notion or logical sense. Like if you want to deal with the I-type path, right? Let me see if I have an I-type example. Okay, I'll not go through the example, but just to give you the idea. So this is the I-type path. And see now here, the question become like, we have all these different control signal, including lot of muxes, multiplexer came in the picture. So we need to make sure that we hold on to this multiplexer control signal, especially for the data selection or operand selection for the ALU, right from the beginning of the EXE till it is written back. So EXE, mem, write back, in these three stages, we must hold this logic, this ALU selection logics stable. This ALU selection logic, like ALU selection 3, data selection 2, ALU selection 2, etc., etc. Those things needs to be, not data selection. This is going to where? Register file, sorry. ALU selection 3, ALU selection 2, that must be stable, okay, for the I-type path. And there are a lot of other multiplexer need to be considered, along with the register file control, data memory now come into the picture. We have the PC load anyway. Those kind of things you need to consider instruction by instruction. And similarly, if we now combine them together in a complete data path, which supports all type of instruction, R, I, J, all these kinds, then we have many control signal to control and set it to the correct value at the correct execution phase. That's the main challenge of computing it. And this combination of this control signal is called a micro instruction. So each phases, like instruction fetch, instruction decode, execution, memory, and write back, each phases, controller issues a micro instruction to the data path to act up. Okay, so each time it computes a micro instruction and send it. So on the project 3, you'll be dealing with that part. Question.
Ooh, can we ask a new question?
Sure.
I don't know if you're done with all the ones in the doc. They should probably go first, but if so, we were wondering about this question from the midterm, or no, sorry, not from the midterm, from quiz 2. You are designing a sequential digital circuit with 12 states and 4 primary inputs. How many minimum number of rows do you need in the truth table?
Oh, okay. So basically, it is to deal with. Let me see. It is to deal with the number of states and then the number of inputs, right? So basically, we need to approach this way. Okay, so let me.
I just put it in the chat too. I forgot that I could just write it. Because the way that I did it and the way that a couple other people did it wasn't how you solved it in your explanation. So it made me think I just kind of accidentally got it and I wasn't doing it the right way or something.
Let me try to in generalize this. Let's say n is number of primary input. Primary input, and S is number of state you are dealing with. Number of states you are dealing with. Okay. So let's say you have like 3 input. Okay, let's not do the exact example. Let's just do the theory. So number of primary input n means this will give at least 2 to the power n rows without considering number of state, right? Now, if you want to combine this number of states, which is like, let's say each combination will give rise to 2 to the power n rows. So it will be, I think, this multiplied by 2 to the power n. Is that the way you guys did that one?
Yeah, I think that's what a lot of people were saying. And then like in the explanation, it was like a lot more complicated. So I was just a little confused about that.
Okay, let's look at that one. Okay.
I can put it in the chat too. That was the most recent one was your explanation.
Okay, let's see.
Sorry, that 4 times 24, it's just the formatting got messed up. And there's a 28 too. That's supposed to be 2 to the 8 and 2 to the 4. So that's just more confusing, sorry.
Yeah, so basically, this is the, okay, I see the points here. So this is more like from a truth table construction perspective, like what it is saying all is this, that number of bits, B is log base 2 of S, right? Then if you just think from pure truth table perspective, you have B plus N, number of bits, right? In the truth table. So that gives you B plus N, this many rows anyway, right? And then some of them are don't care, and they don't appear. Don't appear in the table. So this is more like explanatory way, exactly what is going on inside the whole problem. Whereas this guy is more like an, like blindsman process, like a blindfold step. Hey, you have number of state, number of primary, this is a formula, S multiplied by 2 to the power n. But point is, why is that? And from the truth table construction perspective, then this complex thinking comes up. So that's what I think I have given in your answer to how that internal things is going on and as an explanation. But this is good enough to do, like this S number of states, you basically multiplied by 2 to the power n combination, that many combination, that many rows will appear in your truth table.
Sorry, Professor. So the result from 2 to the power of B plus N is equivalent to the S times 2 to the power of N?
Not really, unless if you have don't care in your term. Let's say your S is equals 16, then these guys will hold together, right? Then they are equivalent, because then B equals 4 in that case. But if S equals 10, then your B is still 4, but you have like 6 of don't care states. So you need to subtract it out of, so 2 to the power B plus N minus number of don't care state. Number of don't care state would be 6 in this case. So that will be equals to your 2 to the power N in that point. So Catherine, if you want to make a generalized equivalency of this thing, I believe it would be like B plus N minus number of don't care. Let's say that is X equal S by 2 to the power N. That would be your equivalent statement. So this is a number of state. So yes, I think, yeah, there are like different style of thinking. And sometimes I admit I do think in the complex way to follow the real steps inside it. But there can be some, like straightforward, also easier explanation as well. So if you find those things, I encourage you to come up to me, like, and tell me. Okay. Is there anything else?
I mean, do you want to stick around?
It's already over. Like,
yeah.
Yeah. What kind of question you have?
I just wanted to go through counting up the number of nands, and yeah, like if you wanted to build an unsigned combinational divider with all nands, how many it would be, I guess, or if you wanted to build it normally.
Yeah, you can. Okay, why don't you put that thing in the discussion, and I can take a look.
Nope.
Knows.
Sounds good. Thank you.
Yeah, it's up to you if you want to share. If you don't want to share, then of course you can send me a private email. That's also okay.
Sure.
Either way.
All right.
Okay, all right then. So I think let's stop at that point, and good luck on your midterm. Remember to collect the, what is that, call-in number for the Zoom. In case you have question during the exam hour, you can use your telephone to connect to the Zoom meeting. Same session, like this class session, I'll be available to reply to any of your questions.
Sorry, do you mean we literally would call you, like using
Yes,
our, like,
yes,
okay. So not like Zoom and then connect via a phone number.
No, you cannot, because you're on the like this thing.
Well, but Zoom has, like, if you're wanting us to use our phones anyway, Zoom has an app on iOS and Android. So that's why I was.
Yeah. That would be an option, but yeah, you can definitely use that if you want. But other than that, let's see, you don't have that bandwidth or anything like that, then you can actually call in through the telephone. So go to the invitation of that, like after the registration, you got some email from the Zoom, right? That here is a link, here is this and that, a 1 page long instruction. And there it has a call-in number, like 800 number, where you can call in from the phone, any phone, you don't even need to use a smartphone. You can use any phone to call in the number and type in the meeting ID or something and type in some PIN. It's all there in that specific instruction set. So you can dial in as well.
And it's just our regular weekly meeting?
It's a regular weekly meeting, yes.
Okay, cool. Thank you.
Just join the Zoom session from your phone.
Was that? Yes, that's what I'm asking. You can join through the phone.